Hello everyone, welcome to my channel. I'm an electronics engineer and I love working on electronics projects in my free time. In this video, we're going to understand how LCDs work and how to interface them with a microcontroller step by step. I will be using a microcontroller from Texas Instruments for this project as they are a market leader in analog and embedded solutions. The device I'm using is part of their portfolio that comes with an integrated LCD controller. This is very useful because it eliminates the need for any external circuitry to drive the LCD. As you can see on the screen, this microcontroller includes a 12-bit ADC, a comparator, an LCD driver, and VBAT support. VBAT acts as a backup power supply typically connected to a battery. So, even if the main power is lost, the device continues to operate and can retain important data in memory. These types of microcontrollers are commonly used in applications like energy metering. I'll cover these features in more detail in upcoming videos, but for now, let's focus on understanding how the LCD works. Before we interface the LCD, let's quickly understand how it actually works. An LCD or liquid crystal display does not generate light on its own. Instead, it controls the light passing through it using liquid crystals. When no voltage is applied, the liquid crystals are twisted, allowing light to pass through, so the segment appears on. When voltage is applied, the crystals align, blocking the light, and the segment appears off. In a segment LCDs, each segment is controlled using two signal, COM and SEG. The LCD is driven using AC signals, and the segment turns on or off based on the voltage difference between COM and SEG. If both signals are in the same phase, the segment remains off. If they are in opposite phase, the segment turns on. Now, generating these AC waveforms manually is quite complex. You need precise timing, multiple signals, and proper multiplexing. This is where a microcontroller with a built in LCD controller becomes very useful. With an integrated LCD controller, the microcontroller automatically generates all the required waveforms for common and segment lines. So instead of designing external driver circuits, we can directly connect the LCD to the MCU. In the next section, we'll see how to configure the LCD on a Texas Instruments microcontroller and display data on it. For this project, I am using the MSPM0 L2228 microcontroller. I also ordered an evaluation board or EVM from the Texas Instruments website. An EVM or evaluation module is a development board that helps us quickly test and prototype with a microcontroller. As you can see on the screen, this board includes the MCU along with an integrated LCD, which makes it very convenient to experiment and learn. The board can be easily powered using a USB connection, so no additional power setup is required. Now let's take a look at the EVM documentation to understand its features and how the LCD is connected to the microcontroller. This is the EVM user guide. As you can see here, the board includes a USB to PC connector for power and communication, a reset button to restart the microcontroller, and an XDS interface for programming and debugging. We also have the onboard LCD, which we'll be using for our experiments. Now let's move on to the schematic to understand how the LCD is connected to the microcontroller. Now, looking at the schematic, we can identify several important sections of the microcontroller. First, we have the VBAT pin, where a battery can be connected. As explained earlier, this allows the device to retain data and continue operating even when the main power supply is removed. Next, we have the main supply pins VDD and VSS, along with the reset pin used to restart the MCU. We can also see SPI communication lines, ADC input pins, and an external reference pin V reference for the ADC. Now, focusing on the LCD, you'll notice pins labeled like LCD underscore 20 and LCD underscore 43. These pins can be configured as LCD segment or common lines. This section here shows how Texas Instruments has mapped the MCU LCD pins to the onboard display. The LCD used on this board is a 28-pin LCD, out of which 24 pins are used as segment lines and 4 pins are configured as common or COM lines. Moving on to the software side, I am using Code Composer Studio for writing and loading the code. You can download it from the TI website. Along with that, you will also need the SDK, which provides drivers and example projects to get started quickly. Now that we have installed all the required tools, let's go ahead and try it out. I will start by importing an example project from the SDK. In Code Composer Studio, go to File, then click on Import. Next, navigate to the MSPM0 SDK examples. Select the L2228 device and choose the LCD example project. Finally, import the project into the workspace. Now let's build the project and check if there are any errors. As you can see, the build completed successfully and there are no errors. Now let's go to the main code and take a look at the implementation and configuration. As you can see, the project already includes several LCD related functions. This function is responsible for displaying a character on the LCD. In this section, we are enabling the LCD module and configuring the common and segment lines according to the LCD hardware. This configuration is important because it defines how the MCU maps its LCD pins to the actual segments on the display. This line introduces a delay in the program. The function creates a delay of approximately 1 second. This is because the CPU is running at a clock frequency of 32 MHz, which means each clock cycle takes about 31.25 nanoseconds. So when we delay for 32 million cycles, it results in roughly 1 second of delay. Now let's go ahead and flash the code onto the board and observe the output. To do this, click on the debug icon here in Code Composer Studio. This will build the project, load the firmware onto the MCU, and enter debug mode. Once the code is successfully loaded, we can run the program and observe the LCD output in real time. As you can see, the code is currently paused at the beginning of the main function, around line 196. Now, I'll place a hardware breakpoint at line 233. This will allow us to pause execution at that point and observe what is actually being written to the LCD. Once the code reaches this line, execution will stop and we can inspect the LCD data more closely. As you can see, the LCD is currently displaying 0, which is expected based on the code. This is because we have only executed up to line 232, where the 0 character is written to the display. Similarly, if we execute the code up to line 245, you can see that the LCD display the numbers 0, 1, 2, 3, 4, 5. Now let's take a deeper look at how the LCD is displaying these characters. You might notice that 0 appears on the left side. This is not random. It is completely determined by the LCD segment mapping, which defines how each digit position is connected to the MCU. As you can see from the code, pin 1 is mapped to these 4 LCD pins 55, 56, 57, and 58. As you can see in the schematic, these 4 LCD pins are mapped to PC6, PC7, PC8, and PC9. These correspond to LCD pins 25, 26, 27, and 28. Now, if you observe the display, these pins are connected to the leftmost digit position. That is why the digit 0 appears on the left side. The display starts from this position based on how the pins are mapped. Now, let's modify the code and display something different on the LCD. Let's try displaying YouTube. I'll update the code accordingly and comment out the lines that are not required. So this is the modified code. I have already loaded it onto the device. Now let's run the code and see what we get on the LCD display. As you can see, the LCD is now displaying YouTube correctly. Similarly, we can interface any segment LCD with a microcontroller by configuring the pins as LCD functions, mapping them correctly, and writing the required data. I hope this video helped you understand the basics of LCD interfacing with a microcontroller. In this video, I focused on the fundamentals. I did not cover advanced features such as low power modes, high power modes, or external resistor configurations supported by Texas Instruments devices. I highly recommend going through the datasheet to explore these features in more detail. If you found this video helpful, please share your feedback in the comments. Also, let me know what topics you would like to see in future videos. Thanks for watching.